second speaker this afternoon is Junliang Shen, and talk about Chern classes, perverse filtrations, and Fourier transforms.
Okay, thanks for the invitation. This is actually my second time to be at Cambridge. The first time was like 6 years ago when I was a graduate student in Zurich, and I visited a local friend here, and I learned to pound. And after 6 years, I came back again yesterday. I tried to pound, and I found my pounding skill was not improved somehow. Hopefully, my mathematical understanding was improved a little bit in the last 6 years. Okay, so today I'm going to talk about the interactions of these three things which I will introduce. So let me start with the motivation, which I will be a little vague. So the main phenomenon I'm going to discuss is called P equals C, which I will describe what it is exactly. So first, let me be by saying that this is a phenomenon of the match of two seemingly very different structures for certain modular space of stable sheaves. M. So I'm not telling you immediately that what M is, but I'll give examples. Okay, so there are two structures. One, the first structure is called perverse filtration, which is given by, so these are two structures induced by two different structures of these modular spaces, as we will introduce in a minute. So the first one comes from the topological, so maybe I just perverse filtration. Or more precisely, people sometimes say the perverse Fourier filtration. This is the increasing filtration on singular cohomology, which is associated with the perverse Fourier spectral sequence. So this usually is carried by, induced by some extra structure of this modular space, which is something like a torus vibration. So the modular spaces we consider will admit a torus vibration with singular fibers. So it's something like M2B, whose general fiber will be just tori, and over some singular locus there are, the discriminant locus there are complicated fibers. But nevertheless, from such a vibration, then you have some structure on singular cohomology that measures the complexity of this vibration, in particular the singular fiber. So this encodes the topological information of the vibration. I give it a name, F. Okay, so this is the first piece of structure that we can look at when your model of sheaves, for example, admits such a morphism. And the second piece of structure is more algebra geometric, which is called the Chern filtration. So this is governed by viewing M instead of the total space of a torus vibration, you view M as a modular space of sheaves. So usually over M, you can find some universal family, and using the universal family, you can actually filter the cohomology, which I will introduce in a minute. But let me just say that it's governed by universal family and the structure of tautological classes. Okay, so these two are two very different structures in general, but in certain cases that these two structures are matched perfectly. So let me start with some examples. So the P equals C phenomenon means that in some cases these two very different structure, topological structure and this algebra geometric structures are matched. So example 1. So this was first, to the best of my knowledge, discovered for the Qizheng system, the Qizheng modular space. So to say that we start with a C, it's a Riemann surface of genus at least 2, and we can consider the Qizheng modular space of rank n, degree d, with the co-prime condition. So then we don't have to worry about the strict semi-stable locus. So now we consider M to be the modular of stable, slope-stable Higgs models. Which themselves are pairs E and theta, where E is a vector bundle, a holomorphic vector bundle of rank n and a degree d, and theta is an endomorphism of this bundle twisted by the canonical line bundle of the base. So, so then the two structures are pretty clear what the meaning of them on this modular space. For example, the first structure, the perverse filtration, is induced by so-called Qizheng system. So M admits a torus vibration, which is in this case a Lagrangian vibration, known as the Qizheng vibration or Qizheng system, from M to some affine base, which I still call this B, which is abstractly isomorphic to an affine space of half dimension. Okay, so then the filtration in this space is, let me just introduce this quickly. So, so we can consider the singular cohomology of M, which by basic homological algebra is the same as the hypercohomology of the base, taking value in a constructible complex given by the push-forward complex of the constant sheaf of M. So these two describe the same vector space, but the right-hand side, by viewing this is a hypercohomology, it carries extra structure. For example, you can apply. So the study of this structure, RH lower star, QM is the subject of the so-called decomposition theorem of Bailey, Sunfirst, Zerlin, and Garber. And the cohomological shadow it carries is an increasing filtration. For example, if you take the perverse truncation functor here, this filter this object by a sequence of direct subcomponents. After taking global cohomology, this gives you an increasing filtration, which is exactly the definition of the perverse filtration. So in other words, this sees the complexity of the morphism, the Qizheng system, from M to B. Okay, now I move to the second structure, which is actually it's more classical, which is the structure of the tautological classes. So this kind of thing has appeared in many of the sheaf, the model of sheaf problems. For example, here, so if you consider M as a model of objects on C, then there is universal family over the product, which I denoted it by U. So this produces natural classes on M. So this gives you natural classes. So I will use the notation C, K in the gamma. So here the K would be just integer, a natural number, and the gamma will be some cohomology class on the first factor of my surface. And then the natural class you can put here is you take the case Chern character of the universal family, which in general would be dependent on which U you choose, but there is a way to normalize it to kill this ambiguity, and you integrate it over the gamma, which is on the first factor, then you end up with a class on the modular space, the Hitchin modular space. Okay. So these kind of in other words, these are actually Kunis components of the Chern characters of the Chern classes of universal family. So these tautological classes were studied firstly by Atiyah-Bott for modular space of vector bundle, and the relations were first formulated by Mumford and many other things. It's studied by many people. So in Davesh theory, these people also call this the descendant classes. And okay, so now I'm going to do, so once you have these classes in the cohomology of the modular space, then there's a natural thing we can do, which in some sense is not that natural, but let me just write down what's the meaning of the Chern filtration. I'm describing an increasing filtration on the modular space, and by the kth part of this filtration, I take it to be the span of the product of tautological classes. So all possible products where the only thing I control is the Chern grading. So so here, so each ck gamma is just a Kunis component of this universal class. So there I only remember which Chern class you take for this Kunis component. So in particular, this filtration, I just filter it by the Chern grading. So I require that you consider all monomials such that the total Chern grading is bounded about by this k, which is the same number here. Okay, so this is a very concrete filtration on the singular cohomology, which is induced by the universal family. And a surprising fact, which is now a theorem, is that in this case, this perverse filtration, which is the topological invariance associated with the Hitchin system, is perfectly matched with this Chern filtration, which is induced by a universal family. But this is actually, historically, this is not how it was formulated in the first place. So the purpose for proving this is to understand a conjecture called P equals W conjecture in non-abelian Hodge theory. Which says that under the match of the underlying topology of the Hitchin modular space with some other modular space in algebraic geometry called character variety, then the conjecture says that the perverse filtration here should be matched with the double indexed weight filtration with respect to the mixed Hodge structure of this affine variety. So I'm not going to go into this direction, but I'm saying that the reason for that motivate people to understand this P equals C phenomenon for this modular space is precisely to understand this match. So in other words, we use some very concrete classes that come from the universal family to understand both sides. So this is, of course, this is not proven. We are proving a P equals C match, so this conjecture, of course, is conjectured by De Catado and Migolini about 15 years ago. So they conjectured it and proved this for the rank 2 case, and it was proven 2 years ago with Davesh Maulik, and also independently by Maulik, Minas, and Schiffman. And all the proofs, actually, both proofs are to understand the P equals C. Using the structure of the tautological classes to understand, to match both filtrations. And so last year there is a third proof, which is in the joint work with Davesh Maulik and Qizheng, is that we try to used a perspective of Fourier transform to see that try to understand this phenomenon, where the P equals C match is really from. So this is to use Fourier transform. And this is what I'm going to discuss for the rest of my talk.
Is this new proof really independent of the other proof?
It uses, so there are two parts. So it uses certain steps which reduces, it reduces the total Hitching system, from the total Hitching system to certain locus with integral curves, which is by adding parabolic spaces. This was also used here. And then the other part, which is to locate the tautological class in the right piece of the perverse filtration. So this is completely independent. And these two are very independent. Yes, Richard?
So are we allowed to restrict this conjecture to this P equals C thing, to the cotangent bundle of the moduli bundles on the...
I'm going to talk about next example, which is exactly to remove this constraint.
Okay.
Yeah. So this is the first phenomenon that I will discuss about it. And the next one, is there any part of the blackboard of this one I should avoid?
Yeah, the lows.
Here?
Yeah.
Maybe I just avoid this at all. Okay, so maybe just let me write down example 2. So example 2 is the phenomenon for the Leboutillier modular space. So here we see that this is a torus vibration, which is indeed a Lagrangian vibration, but now we consider a slightly different situation where for example, we consider that the space we consider is P2, and we fix two integers, d and chi, which play the same role as the rank and the degree here. We assume that they are co-prime, and then so the modular space we consider here is the modular of one-dimensional stable sheaves F, where you fix the fitting support to be a degree D curve, and you fix the Euler characteristic to be chi. Yeah, actually, where I push up, more spaces is visible. So let me continue. Okay, so in this modular space, this is certainly not a holomorphic symplectic manifold, but let's look at here. But it carries similar structures as 1 and 2 as I wrote here. So the structure 1 is the Hilbert-Chow morphism. So here we consider the modular space of one-dimensional sheaves, but we can take the morphism, which only remembers the support of the curves, the sheaves. So this F to the support, the supporting cycle. And so this morphism, the geometry of this morphism looks similar to the Hitching space. For example, if you consider a general degree D curve here, then the corresponding fiber is isomorphic to the Jacobian of this curve. But when this curve is becoming more complicated, it's more non-integral, then the corresponding fiber is becoming complicated. But nevertheless, by the same definition here, we can, so because of this morphism, Hilbert-Chow morphism, so the cohomology carries a perverse filtration, which is the increasing filtration on this vector space. So one of the motivation for studying this perverse filtration, because this is, you can think of this as the cohomologically categorified, it's a categorification of refined Gopakumar-Vafa invariance. For the Calabi-Yau threefold given by the total space of the canonical bundle. So this is also called the local P2. So here we don't have to worry about the vanishing cycle and orientation data also because this modular space is smooth. Okay, so this is the first structure that we talked about. And then the second structure is the Chern filtration. So here the problem is slightly different. So we consider the modular space of sheaves on P2. So a universal family is actually a torsion sheaf on P2 cross M. So this is supported. So this is supported code dimension 1. So then when people do a DT theory, so for defining the descendant classes, we have to make a shift. So again, we have to normalize at the end. We take the Chern character of this F, but instead of just taking the case Chern grading, we take 1 plus k, where this 1 exactly is the reason for the codimension shift. And then you integrate this over a power of the hyperplane class Hj. So we define this to be Ckj. So you see that the definition is exactly the same as, well, it's parallel to what I did in the Hitchin modular case. And using these tautological classes, we get a filtration on this modular space. So if we only stick to the case of Hitchin modular space, then you may think this is too special because there is non-abelian Hodge correspondence, the character varieties and many other structures. But now if we move to P2, then most of these structures are gone. And the only thing that remained is basically that you have the perverse filtration given by the Hilbert-Chow morphism, and you have these tautological classes.
Is every cohomology class tautological?
Yes, due to Boville, I think in this case. In the Hitchin case, this is due to Markman, which says that the filtration will exhaust all the cohomology classes.
In this case, how did the dimensions work out? Is the base bigger than the dimensions of the fiber or smaller?
The base is much bigger than the fibers.
Much bigger.
For example, the case D equals 3, then the base is like 9-dimensional, the fiber is 1-dimensional.
Right. Yeah. So for this kind of thing to hold, you want like a large dimensional base? Like that direction's better than the other direction?
I'm stating the statement and then. Yeah. So the conjecture. So this conjecture, let me first state the conjecture and say the history of it. So the conjecture says that, the perverse filtration and the Chern filtration, which are the two very different structures on this modular space, are matched for M. So this conjecture was first made by Kononov, my student Waiter, who is here, and myself for a certain range where there's no tautological relations between these classes. And at that time, the motivation for making this conjecture is to understand or to categorify a product formula for the refined Vafa invariance for this local P2. And then the last year, I think maybe this year or last, is this year? Okay, sorry. This year, then Kononov, Wunan, who's here, well, all these three people are here, so Moreira, and my student P, they further conjecture this match actually is beyond the range where the tautological relations, the non-trivial relations do not happen. So it's really a match of the total cohomology. So in other words, one can use a very concrete filtration, the Chern filtration, to calculate the perverse filtration. So one of the key difference between these two geometries is the following. So here, if one knows a little more about the Hitchin modular space, then actually we know that the structure of the tautological relation is very special for the Hitchin modular space. For example, it's homogeneous with respect to the Chern grading. this means that when you see a tautological relation, it doesn't matter which representative. For example, if you have the product of the two tautological classes equal to a third tautological class, it doesn't matter which, because the Chern grading is a grading for the Hitchin modular space, so it doesn't matter which representative you use. But here, to make this conjecture true, this relies heavily on actually the structures of the tautological relations for these classes. So this conjecture was, let me just say a few words, so as I will explain, this is, so in the work with Davesh and Qizheng, we know that this is, so the perverse filtration is larger than the Chern filtration when the cohomological degree is some linear bound dependent on the degree. And then Yao Yuan, who showed that using the intersection theory on Hilbert schemes, she showed that it's true for H4. This is the first non-trivial degree. And then in the very nice paper of the KLMP, so they study carefully the geometry of the relations on this modular space, and among other things, so did a lot of work in this direction. And one of the consequences that they check this conjecture for, so this is dependent on D and chi. This is for any D grade bounded by 5. So then, so by combining with the MSY method, my student and I, we are able to show that this is actually a match true for H, again linear bound. This is the perfect match for some linear bound on D, which will imply actually the original asymptotic formula for the numerical invariance.
Can you say something about where the relations start showing up?
Here. So, I mean, these are the generators, and then the first relation starts at 2D minus 2. If I'm correct. Oh, 2D. Okay. 2D.
But the conjecture is that it's smooth for
Yes.
degree.
Yeah.
There's no bound with.
There's no bound. You can ask Miguel if he still believes this conjecture. Yeah, the conjecture is for every. There's no bound. There's no bound for, and this is for the entire cohomology. Yeah. So if you consider the modular space of degree 4 and 5, then this conjecture is already very complicated because, as Jean pointed out, the perverse filtration will, because the fibers are small, so the perverse filtration will terminate very early. The length of perverse filtration is very small, but a priori the Chern filtration could be very long. So the reason that if they are matched, this suggests that there are a lot of tautological relations between these classes which can help you to kill down to reduce the Chern bound. And even for this consequence, it's not so obvious to me. Yep.
So M here is as in example 2,
Yeah,
or is it more in?
This is for P2. And so the first so example 1 is the Hitchin modular space, and example 2 is the Le Boudier modular space associated with P2.
Is the conjecture also different?
At what? No, this is for P2. Yeah.
I mean, do you have the conjecture for more general surfaces?
Yeah, essentially for more general del Petzl surfaces, it's essentially the same thing. The reason we work on P2 is because this is the first the example. In this case, there's only one curve class, so it's clean. You can stick to figuring out what's the correct. And but for general type surfaces or for other surfaces, then the situation is probably more complicated. For example, it's not clear that the singular cohomology is the right thing to look at from the perspective of BPS invariances. So here, secretly we are. So here, for example, for this sentence, So this perverse filtration categorifies the refined PPS invariants. This is actually a consequence of local diapason surfaces. Otherwise, you should consider that, you know what one should consider.
You mean the filtration does not exist for other things, or is there some problem?
You can define it brutally, but I'm not. You just imply the perverse truncation factor. You can define it, but it's not clear that the structure is good or not.
You could formulate this, I guess, for any versal family of curves and a compact line Jacobian.
Yes, this is what we're going to do. Yes.
Yeah.
Okay, so the rest of the talk, I'm going to explain at least how I think about this phenomenon. So let me start with a toy example. So now for all these modular spaces, the common feature is that it's a torus vibration with degenerated fibers. And by looking at if we look at such a modular space, such a geometry, then one of the first thing we can do is we can ask ourselves what happens if we abelianize the question. Namely, we just delete all the singular fibers and just look at the abelian part and what this phenomenon is saying. And surprisingly, this is actually it's related to a very different story, which is the theory of Fourier decompositions for abelian schemes. So let me start with an intuitive model of how I think about this phenomenon by using abelianization. So this is a little cheating. So I'm not abelianizing the modular space, but I'm abelianizing the question. So now we consider just the simplest example we can have for torus vibration, just namely we consider just abelian scheme. Over B. And assume the relative dimension is G with the smooth space, as always. So in this case, the special geometry of this torus vibration tells the two things so this A actually carries two structures which are corresponding to the two properties I said. So the first structure is, so because we're considering the abelian guys, so we have there's a group structure. So you can add 2 points, torus, and this group structure, it buys us actually an understanding of the perverse filtration. Well, actually, in this case, it's just the Laue filtration because there's no singular fiber. So the second structure, if we have a torus, we can consider it dual torus. So this is a duality. And so the duality actually can help us to access the Chern class, the Chern classes. So in other words, in this abelianized world, the match of the Laue filtration and the Chern filtration actually is a match of the two structures, the group structure and the duality structure. So let me elaborate this. So let me start with one. So the group structure is encoded by the morphism. For example, we can consider the morphism of multiplication by n. So we pick some integer which is greater than 1, and we can consider the multiplication by n. So in particular, so this is just map every point for that corresponding abelian fiber. It is set to n times this x, and then it gives you a linear operator on the singular cohomology. Oh, by the way, so everything I'm talking about here was done by Fourier and Moore in the 80s. So in other words, if you use this perspective, then the P equals C phenomenon actually was already discovered in the 80s. So we have this. So the multiplication by n operator acting on the singular cohomology of this total space of the abelian scheme. So the key fact proven by them is that this operator is diagonalizable over the rationals, which induces for the rational cohomology a weight decompensation. So far we are talking about linear algebra. So you have a linear operator which is diagonalizable, so we can consider the weight spaces. Okay, so a few facts, a few properties concerning this decomposition. So this is actually the cohomological version of so-called Bourvil decomposition. So a few facts. The first is that, so this I is the weight I space, meaning that if you use this, you pull back along the multiplication by n. This is n to the power of I. It's the eigenspace. Okay, so the first property is that. So the decompensation is multiplicative under cut product. This is obvious from the perspective of weight spaces. So you have Hi comma Hj, then obviously it will go to Hi plus j. Okay, so this is the first property. And the second is that, so this weight is really the weight in the Leray filtration. So star splits the Leray filtration. So you have a multiplicative splitting which splits the Leray filtration. So if you consider the Leray filtration, the case piece, and this is nothing but you just collect all the weight spaces with weight small or equal to k. So the third property, so in other words, so if you're not very comfortable with the perverse filtration, you can think of this as a generalization of the weight we're talking about here from the torus perspective. And the third is that this decomposition is independent on the choice of n as long as n is greater than 1. So no matter which n you're choosing, it's the same decomposition, which is intrinsic. Okay, so this is a very good understanding of the Leray filtration, which is the Leray filtration is nothing but just you consider the weight spaces with the weight small or equal to k. But now let's see how this interacts with the Chern classes. This requires the idea of duality. So now we consider A over some base, but we can borrow its dual, which is the relative pick 0, the dual vibration. And starting with the work of Mukai, so people have thought about the derived equivalence between these two varieties, which is induced by some universal object, universal sheaf, universal line bundle called normalized Poincare line bundle. So this is A cross A. It's on the relative product. And once you have an object, the formula kernel on the relative product, you can view this as a correspondence in K theory. So in particular, you can. So if I define F, which is considered to be the cohomological for a transform, to be the total Chern character of this line bundle L. So this is in other words, it's just exponentially e to the power of C1 of L. So this is a mixed degree cycle on a relative Chow group of A cross A dual cross A over B. So in particular, this gives you, so you can talk about a correspondence induced by this F. So then using this duality, we see actually the Chern grading, how the Chern grading comes up. So if we consider the A side, and we want to understand the case weight space, this is nothing but the image of, you just take this, so this is a mixed degree cycle, and you just take its degree K part. Because this is a total Chern character, you just take the Chern K. And you can use this to apply to any cohomology on a dual side. So the weight K space is exactly the image of Fk. So in other words, maybe I, right here. So in other words, the Kunis component of Chern K of the universal bundle the Kunis components of Chern K have weight K. So, okay, so then combining these two, if we have these two geometric ingredients tell us exactly how to think about the Lorentz filtration. So you have a natural splitting, natural multiplicative splitting, which is basically the weight spaces and detect the Lorentz filtration. But on the other hand, by looking at the duality, then you see that how this sees the Chern classes. Okay, so any questions so far?
When you see the Chern classes of the universal, of the Poincare line bundle, right?
Yeah. So what's the weight of a class? Really, it depends on it is the Kunis component of which Chern K.
I mean, it's different Cherns.
It's
We have a universal object. Yeah.
It's not a different Chern. For example, if you consider this a family of curves which map to a fixed curve, then you can, by a Riemann calculation, you can the previous tautological classes are closely related to this, or not closely, but exactly this Chern. And then, for example, the shift 1 in the P2 case exactly comes from the Riemann. The universal curve is of codimension 1 in this product of P2 cross the M. So it's the same Chern. What I'm saying is that, but here the story is oversimplified because we have deleted all the singular fibers and just remembering the group part.
So if I identify Fourier-Mackay transform tells me something about how the cohomology of A and A can relate.
Yeah.
What happens to the filtration if I move it?
Yeah, so the better way to think about it is that the Fourier-Mackay is stable under this decomposition. So a certain ith-graded piece will be sent to another, like 2G plus 2.
Complement.
Yeah, exactly. Then if you understand everything in terms of the decomposition, then of course the filtration is just shadow. Okay, so now let's move to the case of the singular fibers. As Jim suggested, I will focus on the case of compatible Jacobians. So, because this is a common geometric setting in both stories I mentioned earlier, that so when the singular fibers of the Hitching system, also in the Leboutier spaces, come from the degeneration of curves to certain a family of smooth planar curves to singular curves with at worst planar singularities. So let's. Let's talk about the compatible Jacobians. So just a quick review is that if we consider C to be a smooth curve, then the Jacobian is just it's just a complex torus. But if we consider X to be an integral projective locally planar curve, by this I mean you consider the singularity, you require the singularity locally using analytic topology can be embedded into C2. So then in this case, if we consider the modular space of line bundle of a fixed degree, so this is no longer a proper abelian variety. So it would have open part, but it can be compactified by, so this is the locus of line bundles, but you can consider rank 1 torsion-free sheaves. So since we assume the curve is integral, so no stability condition is needed, the upshot is that this is still reasonably nice. So this is a Saryski dense. So if we allow ourselves to have more singularities than the planar ones, then certainly, so the complexity of the compacted Jacobi is no longer, it's almost the complexity of the Hilbert schema points on the threefold singularity, which is a monster. So that's the reason we, and in that case, maybe the right thing is not, the right thing to look at is not the singular cohomology, but maybe you have to do the BPS cohomology or so, involving the vanishing cycles. But nevertheless, we focus on the case with it works the planar singularities. Okay, so now instead of looking at a single curve, again, as Jim suggested, let's put in family. So we work over a generic setting by only, so we consider a family of curves of this kind, and with the compacted by Jacobian fibration denoted by H. So here, the only assumption I have is that the JC bar is smooth. So the total space is smooth, but of course the fibers could be very singular. So this is particularly, for example, the geometric cases in the previous modular spaces we discussed. Okay, let me start with, so in the previous story, the abelian case, we have a very nice weight decomposition which sees all the structures. And, but now in this, when we add singular fibers, so the question is whether, okay, we expect, so we know from the decomposition theorem of BBDG, Bernstein, Billington, Deligne, and Garber, that we should use, in order to get nice structures instead of a local system of the variation for Hodge structures, we should use the perverse sheaf that arises in the decomposition theorem, which will, instead of, which will replace the Leray filtration by the perverse Leray filtration. But the natural question is whether you still have, after doing this replacement, whether you still have these nice structures here. So let me start with the bad news and a fix of it. So bad news is no. The answer is no. This is the bad news is that there's no weight theory, no weight structure at all. In the following sense, so this is in joint work with Yonghan, Davesh, Prof, and Qizheng. So it says that if we consider that the simplest of singularities, then the entire thing will fall apart. So now we consider the simplest case we can consider is you consider MG bar with, you add one more stratum. So this is the locus where you consider just a smooth curve, genus G curves, and you just consider that one extra stratum given by one nodal curves. This is a smooth stratum. And then over this we have the compacted by Jacobians. So this is a very nice fibration. Although it's, I mean, you have singular fibers, but these singular fibers are stable, so they're not that bad. But nevertheless, we know that if G is at least 3 in this case, then there does not exist any splitting multiplicative splitting of the perverse filtration So, in particular, there's no chance that you can have something like that to happen. So the proof of this theorem is, I call this theorem 1. So the proof of this theorem is through a careful study of the double ramification cycle relations, which gives you some contradiction if there is a multiplicative splitting. So if there is a multiplicative splitting, then you know that certain types of relations should certainly hold. And then you prove these relations are wrong. Okay, but now in the last 8 minutes or so, let me give you how many minutes I have. 10. Okay. Let's continue with the good news. Good news. So in this case, so the thing we know is that there's no multiplication by n. So this kind of thing, it cannot be extended to the singular not easily extended to the singular fibers. So the only thing we have to use is the dual. So then still can use duality. So the idea is that by using duality, we can more or less recover all the things we talked about above when there are singular fibers. But the price we pay is that all the decomposition, all the statements concerning decompositions will be a filtered statement concerning the filtrations. Okay, so let me explain how to use the duality here. So this is the work of Erinking. So if we consider the compacted by Jacobian fibration. And if so that it's J bar cross J bar, but if we only consider J cross J bar, we allow the first factor to only parameterize line bundles. The second factor can still parameterize torsion free sheaf. Then over this, there is the Poincare line bundle actually can be extended. So the complement of this in the total relative product is of codimension 2. This is codimension 2. So then the work of Erinking about more than 10 years ago shows that so this Poincare line bundle actually can be extended to a monster here, which is a Carl-Macaulay sheaf. So there exists a Carl-Macaulay sheaf P. So on this relative J bar over B. Such that if we restrict this to the open, as above, this recovers your L, and further, so P induces derived equivalence.
I think I'm losing track of something simply. Where did the dual Jacobian variety go?
So since this is a Jacobian variety, so you can think of this as a PPAV.
Oh.
So it's a self-dual. And yeah.
Got it.
Okay, so you have the construction of this P is not very easy. So eventually this P is being reduced to the Hyman's isospectral Hilbert schemes in his proof of the n factorial conjecture. But the Carl-Macaulayness of this P exactly follows from the same reason using Hyman space Hilbert scheme. But nevertheless, we know the existence of a coherent object. This is a dB co of this singular space. But nevertheless, since this is bounded, we can take the localized Chern class, we can take the tau classes. So we still are able to obtain the Chow theoretic Fourier transform operators given by this P and the inverse of it. So these are just, but now we are considering singular spaces, so the lower Chow is not the same as upper Chow. There's no, yeah, so we in this case, they are in here.
Say it again, this is the cone we're calling this.
This is just boundedness.
That you have to operate that.
I'm just taking the characteristic classes of this P, but you can view this as a correspondence
But
from.
the characteristic classes, cohomology classes.
You know, in Chow, this is this is you just take the tau class of this P and twist it by some tau. So because this P is not a perfect, this P is not a perfect, but it's still bounded, so you can define the characteristic classes. For example, in the chapters 18 of Botten's book. First, the 6 chapters are not enough, but you have to go through. All right, okay. So now let me state the theorem, which is the good news. So how to still use all the machines when there is no multiplication by n. So this is the second theorem. This is in the work with Maulik and Ying. So I divide the theorem into 3 parts, which convey the 3 different types of information. The first one is the motivicality. So motive. It says that, so first, because one of the difficulty for understanding the decomposition theorem is that, so you have to apply the perverse truncation functor, which is something very abstract. Usually it's very hard to compute. But this theorem says that, so these are given by very concrete algebraic tautological classes. So there exists a decomposition of the relative diagonal into orthogonal projectors pi 0, pi 1, and pi 2g, where g is the relative, the arithmetic genus of the fibers. So this happens in, in the Chow group, satisfying the relation that pi 0, if you consider the composition of 2 correspondences on the right-hand side. So this is either 0 or itself when I is equal to j. So this means they are orthogonal projectors. So there exists a decomposition of the relative diagonal, which after homological realization inducing the decomposition theorem of BBDG. So I'm here using the shift. The shift I'm writing down here is certainly wrong, and I didn't attempt to make it correct to avoid too much necessary shift. So the first, and moreover, let me complete the sentence. 2 minutes, right? So moreover, the projectors, the algebraic cycles on the right-hand side are expressed in terms of this cycle theoretic Fourier transform obtained from the Arrinke sheaf. So the first part of this is actually is a conjecture of Kode and Hanamura on that the decomposition theorem is motivic. And so the second part gives you the formula of this in terms of Fourier transform. So in particular, this pi will see both the perverse filtration by the first part, since this lifts the decomposition theorem, and also will see the Chern filtration by the second part. So this is the first result. And the second is the perverse filtration. The C is containing P. So in this case, as I said, you won't get any results concerning the decomposition because of this reason, but in this generality. But nevertheless, if we consider the image of Fk by taking the case-graded piece, so this will lie in the pk. So in other words, so this is like the Chern k, and the quickness components will naturally lie in pk in the universal way. But still, nevertheless, this only tells you the behavior of every individual tautological classes. And the third one is the multiplicativity. Which says that although there's no decomposition, but like in the abelian scheme case, but the perverse filtration is in this case is compatible with product. So in particular, combining 2 and 3, you can handle a monomial of tautological class, a monomial of the product of tautological classes. Okay, so I'm out of time, so I'm stopping here. Just let me say, so this gives you a general way of thinking about this. The P equals P, at least one direction of the C containing P phenomenon. Then combining with some other tools, this can imply the P equals W for Qizheng system, and also P equals C in a certain range of P2, and also the motivic decomposition conjecture of Cauchy-Hanamura in the case of Qizheng system by further using Springer theory and the nearby and vanishing cycle technique combined with one to deal with these non-integral curves. Okay, I'm stopping here. Thanks.
Questions?
Yeah, so I guess you kind of said it at the end, but so that in the background of this, there's still this move where you have to go to the elliptic locus of the Higgs system to calculate. So how does that play out here?
Yeah, you add one more point. So this is a technique which has been used commonly in the study of Qizheng system, which I think in study the Katz conjecture, this was used by Dubrovka, Ginsburg, and Trafking, and this in the cohomological question was studied by was used by HMMS. So the idea is that you add a puncture, and then you add a parabolic structures there. And then if you make the residue generic enough that the only integral spectral curve will happen there. But then you have to move back to the original Higgs bundle. And in the middle of the process, then, so here for proving these things, you do a Springer theoretic argument, which can help you to reduce it back. So to apply this to all these applications I mentioned earlier, you have to combine it with some other things. But yeah, does that answer your question?
Yeah, so I guess from that perspective, like, what, I mean, so where are you using, for example, like you expect the Fano hypothesis on the surface to come in at some point, right? In that example.
No, but in the Qizheng case, there's no.
But the parabolic thing is a bit like a Fano guy, right?
No, you fix the residue.
You fix.
So again, yeah. So there's a technical subtlety that we can discuss afterwards.
Yeah.
So there are two things. One is that the ranking sheaf was not extended yet to the entire base, and the second is the support of the decomposition theorem for the honest Qizheng system is very complicated by the work of De Catado, Henlos, and Migrolini, which suggested that every possible support, every possible potential support can really be a support there. So here, the idea is that for the second part, we use nearby and vanishing cycle techniques to overcome that. But these are technical things.
So maybe just to help me connect the dots between the first half of the talk and the second half of the talk, I would have expected in this setup to see the universal sheaf on the convectified Jacobian, so something living on like C cross JC in Chern classes, but instead you're using sort of this L. So how do those relate?
No, this is a great question. So, okay, so yes, so that we are trying to handle things here. So this is P is here. And then if this is a family of spectral curve map to a fixed surface or curve, then you are as like a S cross J bar. So this is the more traditional tautological classes you are looking at. and this is the ranking sheaf P. And then, but this is a shadow of this because this is an Abel-Jacobi map which maps C cross JC bar, and this is a finite morphism. So the PF is nothing but the restriction pushed forward. So you can imagine that from the projection formula that all the properties you want from here can be read up from here. That's the exactly. So the universe. This is actually just a pi lower star the restriction of P to this Abel-Jacobi, something like that.
Thank you. Yeah.
So for Bovie decomposition, you have a lot of vanishing. When you fix the cohomology and look at the weights, like half of them vanish and there's some conjecture. Does it also extend, because of the dividing, does it also extend to the general setting?
Yes, so you're talking about the child, right?
Yeah, child, yeah.
So yeah, because a large part, so far today we are focusing on the cohomological story. So a large part of the Bovie decomposition lies in the kernel of this, lies in the kernel of the cycle class map. So we'll expect, for example, so the answer is that we have a conjecture that analog of it. So which suggests, so a priori you cannot. So when you have singular fibers even this simple, you cannot generalize the Bovie decomposition to this setting. But if we the conjecture is that if you have Lagrangian fibration, so then this is a joint work with Yonghan and also Davesh and Qizheng that we expect that there's in that case all this correction term will vanish, and in that case so this is relevant to the Bovie-Voisin conjecture concerning the algebraic cycles on the hyperkähler manifolds, for example.
Other questions? So let's thank you again.